In this section, you'll move beyond a single GPU and learn how to actually scale training. We'll walk through the core ideas behind multi-GPU data parallelism, how to serve trained models efficiently in production, and how to choose between H100 and H200 for real workloads. On a single accelerator, modern deep learning quickly hits three hard limits. First, memory. One device often can't hold all the parameters, activations, and optimizer states of today's large models. Second, compute. Even if it fits, training time becomes impractically long. Third, the input pipeline can't feed the device fast enough. At that point, scaling across multiple devices becomes mandatory rather than optional. Data parallel training is about splitting the data, not the model. You keep an identical copy of the model on each GPU. The global batch is divided into per GPU mini batches, and each device processes its chunk independently, running its own forward and backward pass. At the end of the step, gradients from all devices are averaged and the shared weights are updated. So adding GPUs mainly lets you increase batch size and throughput, while keeping the model definition unchanged. Once you scale training across multiple GPUs, each GPU holds a replica of the model and computes gradients on its local mini-batch. Distributed data parallel uses a communication library, like NCCL, to run an all-reduce. Gradients are summed across GPUs, and the averaged result is broadcast back to every replica. Each GPU then applies its optimizer step locally, using those synchronized gradients, so the models stay identical. To get good scaling, you want as much of that gradient communication as possible to overlap with computation. With multi-accelerator training, the most important knob is the global batch size. Global batch is simply per device batch multiplied by the number of devices. If you double the number of GPUs or TPUs and keep per device batch fixed, your global batch doubles. To keep optimization behavior similar, you usually scale the learning rate with the global batch. This linear scaling rule says twice the global batch, roughly twice the learning rate, assuming you also use a warm-up schedule and watch the loss for signs of instability. As you add GPUs, the interconnect can become the real bottleneck. PCIe is a general-purpose bus, more like busy city traffic. Bandwidth and latency are fine for a single GPU, but gradient synchronization across many devices becomes slow, so additional GPUs give diminishing returns. NVLink is a dedicated high-speed GPU to GPU link, more like express trains between GPUs. It offers much higher aggregate bandwidth, which is critical for fast all-reduce operations and for tensor or pipeline parallelism in large model training. Multi-GPU performance depends not only on how fast each GPU is, but also on how they're physically wired together. In an all-to-all fabric like NVIDIA switch, every GPU can talk to every other GPU in a single hop, so collectives such as all-reduce can scale almost linearly as you add devices. In ring or partial mesh topologies, gradients must hop across several GPUs or fall back to slower PCIe links. That extra hop count quickly turns into lower throughput and poor scaling at larger GPU counts. Training and inference optimize for very different objectives. During training, you can tolerate slower individual steps, as long as the overall job finishes quickly. You use large batches, keep lots of optimizer state in memory, and pay the cost of backward passes. Throughput matters more than single-step latency. Inference flips that priority. Now every request must be fast and predictable. You mostly run forward passes, keep services stateless, and focus on cost and P95 latency per request. Triton acts as an inference traffic controller for your GPUs. It takes many small requests coming from Python, C++, or HTTP and automatically batches them into GPU-friendly chunks, so tensor cores stay busy and latency stays predictable. Under the hood, it can serve models from different backends at the same time, TensorRT, PyTorch, ONNX runtime, while sharing the same H100 or H200 pool. This lets you run multiple models concurrently, mix frameworks, and still keep utilization high in production. A typical GPU deployment pipeline starts with a trained model in PyTorch or TensorFlow, then converts it into a framework-neutral format like ONNX. Once you have that portable graph, you can run hardware-aware optimization passes, fuse layers, tune precision, and apply quantization to FP16, BF16, INT8, or even FP8 where it's safe. Finally, you build a TensorRT engine, a compiled binary tailored to H100 or H200 to get maximum throughput and minimum latency in production. For inference, batch size is your main tuning knob, whether you're on H100, TPU, or Ascend. With tiny batches, each request starts quickly, so latency is excellent, but the accelerator is underused and throughput stays low. As you increase batch size, throughput climbs because the hardware is kept busy. If you push batch size too far, latency explodes and your P95 or P99 deadlines get missed. The goal in production is to find that sweet spot batch size that maximizes throughput while still meeting latency SLAs. H100 and H200 are architecturally very similar, but the H200 changes the game for memory-hungry models. It offers almost double the HBM capacity and a large jump in bandwidth. In practice, that enables larger batch sizes, longer sequence lengths, or bigger models before you hit out-of-memory errors. For workloads like large language models or recommender systems, H200 can reduce the need for model or tensor parallelism and simplify your overall scaling strategy. When you're choosing between H100 and H200, start with a simple question. What really limits your workload? If you're running standard large models, CNNs, or a mix of training and inference, you're usually compute-bound. In that case, H100 gives you an excellent balance of throughput, ecosystem maturity, and cost. If you're dealing with extreme LLMs, huge context windows, or memory-bound serving, H200's extra memory can simplify everything by reducing heavy tensor parallelism, offloading tricks, and complex pipeline sharding. To think about NVIDIA as a platform, picture layers that reinforce each other. At the bottom, you choose hardware like H100 or H200 sized for your model's memory and throughput needs. Above that, the interconnect determines how well multiple GPUs behave as one system, so NVLink and NVSwitch are key for scaling and all-to-all traffic. Your deployment stack, Triton together with ONNX or TensorRT, turns trained models into production services. Finally, DDP with NCCL ties it together so training, scaling, and serving operate as one coherent full stack.